All right, back to topic 1.10, the normal distribution. This is part 2 of this video. All right, so we've done a ton of talking about the normal distribution. Now we're actually going to understand how useful it really can be. So the last thing we left off with was this idea that the normal model is also so standard that we can use technology to find proportions of data values located on a given interval. Now, what the heck do I mean by that? Well, if you are normally distributed, we can answer questions like these. What proportion of data is below a z-score of 1.4? So remember z-scores, 1.4 would be somewhere right around here. Whoa. Sorry, that's negative 1.4. I apologize for that. Positive 1.4, somewhere right around here, right? Remember, here's 0. That's the mean. 1 above, 2 above, 3 above. Very unlikely around here. So 1.4. So I'm trying to find the proportion of the population that would be below that value. Another question is, what percent of data would be above a z-score of negative 1.5? So negative 1.5 would be somewhere right around here, directly between negative 1 and negative 2. And this time I want to know the proportion of data that is above that. Again, that's going to be a pretty big chunk there, right? And I could also answer questions like this, what percentage or what proportion of data is between negative 2.3, which would be right about here, right? And 0.7. 0.7 would be right about here. So it's kind of an awkward shape there, but between those two values, what proportion would fall there? Well, for any just random any random population where I have no idea what its shape is, that would be a really hard question to answer, right? But with the normal model, this is actually a really easy question to answer. It's actually pretty cool. So again, first you have to understand, what am I asking you? I'm asking you for the proportion of data above a z-score, below a z-score, or maybe even in between two z-scores. All right, so how do we do this? Well, we can actually use our TI-84 to find these proportions. So to do this, you have to hit second vars. Then you're going to select the second option down, normal CDF. Your screen should look something like this. If it doesn't look like that, make sure your stat wizards is turned on under mode. All right, now normal CDF speaks in the language of z-scores only. So you got to plug in z-scores here. So the lower value is the z-score at the bottom of the area that you want to find. And the upper value is the z-score at the top of the area. So what normal CDF will do is it'll find you the proportion between two z-scores. Lower z-score to upper z-score. All right, leave the mu and the sigma at 1. That's going to keep us at 0 and 1, excuse me. That's going to keep us universal, right? Because we want to talk in the universal language of z-scores. And when you're speaking about z-scores, the mean is always going to be 0 in the middle, and the standard deviation is always going to be 1. 1 above, 2 above, 3 above, 1 below, 2 below, 3 below, so forth. Now, if your upper or lower limit is infinite, like you want to go way above, all the way above forever, then you're going to use a 99 to represent that infinitely high z-score. Or if we want to start way below, we want to go way below, then we want our lower value to be negative 99 to represent an unbelievably low z-score. Now, those are just numbers that are representing something that's extremely high or extremely low. All right, so you still might be like, I'm not quite sure how this is working or what this is going to do for me. So let's actually, let's go back to this real quick so we can answer these questions. So first off, you got to understand what you're asking. I'm trying to find P, the proportion of data that is a z-score below, so that's less than 1.4. So what I'm going to do is I'm going to grab my calculator. I'm going to go second vars. And then I'm going to choose normal CDF. Be careful you don't choose normal PDF. We will never use that. All right, so what we want to do is we want to start way below, right? Because it's got to go in order lower to upper. So we want to go all the way below 1.4. So again, that's infinite, like all the way down. We don't really have a button for that. So we're going to do negative 99. Negative 99 is just representing a z-score way at the extreme bottom of the tail. Even though we stop at negative 3, technically it does go lower. It's just very unlikely. So we use negative 99 to represent like this most extreme low z-score. And the upper value that we want to stop at is 1.4. So what we're doing is we're asking the calculator to answer this exact question for us. What proportion of data is from extremely low up to 1.4. And it's really cool how it does this for us. All you got to do is hit paste, enter, hit enter a second time, and there it is, 0.9192. So 0.9192, 91.92% of data in a normally distributed population will have a z-score below 1.4. All right, let's answer this next one. What proportion of data has a z-score greater than, above, negative 1.5? Now, some kids always end up asking me, does it matter? What about equaling negative 1.5? You know, greater than or equal to, less than or equal to. The normal model doesn't matter with that, right? It doesn't get impacted by that at all. All right, so once again, we go to second vars here, normal CDF. Now, this time I want to go above. So I want to start at negative 1.5. And I want to go really, really high, like unbelievably high. So that's why we just put a 99 there. I mean, honestly, some kids will put a 3 there. Don't do that because, you know, again, you have to understand there is some values above 3. It's just very unlikely. So we use 99 just to be like this extremely large value, way, way, way towards infinity. All right, and we get 0.939. Make sure you round correctly, so 0.9332. 0.9332. So, you know, here's that negative 1.5 line, and 93.32% of data is above that. All right, what about this one? What proportion of data is between negative 2.3, and there's my z, and 0.7? So again, I'm trying to find the proportion of data that is in between a z-score of negative 2.3 and 0.7. And again, I'm going to grab normal CDF here, second vars, normal CDF. And now again, this time I'm literally looking in between two values. So just make sure you go left to right. Negative 2.3 is on the left. 0.7, whoop, I typed the 0 in opposite here. 0.7 on the right. And hit paste. You got to hit enter twice. So paste brings it to the home screen, and enter one more time. So we get 74.73%. 0.7473. And again, that is the proportion of data in between. So again, this is pretty cool that we could do this because this is true for any population that follows a normal distribution. All we got to do is understand a couple things. Normal CDF only speaks in the language of z-scores. So you got to make sure you use z-scores. But I already taught you how to find z-scores. You just got to use the z-score formula, which is really easy. And the other thing is, you know, when you're showing work on a test or a quiz or homework, what have you, don't ever write normal CDF, right? That's not work. That's just how our calculator figures it out. What you need to show is exactly what I'm showing right here, right? You're identifying what area you're trying to find, below, above, or in between, and then you write your answer next to it. You can write your answer as a decimal or a percent. I don't really care. All right, let's look at like a more specific problem that is actually like specific to an actual real world problem. All right. Example. The mean weight of all boxes of Cheez-Its follows a normal distribution with a mean of 6.2 ounces and a standard deviation of 0.2 ounces. And this actually makes complete sense, right? Like Cheez-Its, boxes of Cheez-Its should all be the same. But we know that, you know, nothing in the world is the same, right? Everything varies. So some boxes are going to weigh a little bit more. Some boxes are going to weigh a little bit less. But most boxes should be really, really close to that 16.2. I can even make a picture of this if you really want to, right? So all we got to do is draw that nice normal model, which, you know, it's not too bad to draw. Right smack dab in the middle is going to go the mean, 16.2. That's going to have a z-score of 0, right? Then we can go 1 above, 2 above, 3 above, and all we got to do is add the standard deviation. So that's going to be 16.4, 16.6, and 16.8. And then we're going to go a little bit below, 16, 15.8, 15.6. And this model makes complete sense. Like most boxes should be near the mean, and very few are going to be overweight, very few are going to be underweight. All right, so let's ask two questions here. What proportion of boxes weigh under 16 ounces? So I'm trying to find the proportion of, and I can even use a C for Cheez-Its, right? The proportion of Cheez-It boxes that are under 16 ounces. Now, if I'm going to do this on my calculator, I got to be in z-scores, right? The universal language of normal model is z-scores. So I got to come to the side real quick here. I got to figure out what's the z-score, you know? Oh, actually, I should know it just by looking, right? It's -1. It's exactly -1. But just to prove it to you, I would take 16 minus the mean divided by the standard deviation, and that's going to be 0.2 divided by 0.2, which is exactly -1. Negative 0.2 divided by 0.2. So basically, I'm trying to find the proportion of boxes that have a z-score less than -1. So 16 is the actual weight of the box of Cheez-Its, whereas -1 is its equivalent z-score. So notice that these two statements are equivalent. One is just in terms of Cheez-Its, or one is in terms of z-scores. But I need z-scores because that's the language that normal CDF works with. So I'm going to go to grab normal CDF, and I want to look below, right? I want to book less than -1. So I'm going to start at -99, and I'm going to stop at an upper value of -1. So this is going to start way down at the very, very smallest of small boxes, and it's going to stop at a z-score of -1. And I get 15.87%, 0.1587. 0.1587, or if you want to convert that, you can. So if I look at 16 ounces right here, about 15.87% of Cheez-It boxes, right? There's billions of Cheez-It boxes out there. I don't know about billions, but millions, right? There's a lot. 15.87% of them will be below that. All right, let's try one more here. What proportion of Cheez-It boxes are greater than 17 ounces? All right, now 17 ounces is somewhere up here, right? So I got to calculate its exact z-score. Again, I'm going to do 17 minus 16.2 divided by 0.2. And again, you need to grab a calculator to do this. Have no fear. 17 minus 16.2. Just make sure you hit enter when you do that top first. You get 0.8 divided by 0.2 is exactly 4. So this is a very high z-score, right? I'm trying to find the proportion of z-scores that are greater than 4. I'm not expecting a big answer here, right? I'm not expecting a large proportion. I can literally see how tiny it is. So I'm going to go back and grab my normal CDF here. And I'm going to go ahead and put in, now this time I'm going to go from 4 to 99, right? I'm going to go start at 4 and go way above because it said greater than. Hit enter twice here to paste it and then find it. And again, be very careful. I hope you guys have all seen this before. Don't just look at the numbers. This e to the -5 means I got to move the decimal 5 times to the left. So 1 time past the 3 and then 4 more times. That's actually going to produce 0.000032. So notice how the 6 tells that 1 to go to a 2. So that's very, very small, right? As a percentage, it's 0.0032%. So a very, very, very small percentage or proportion of Cheez-It boxes are going to be over 17 ounces. And this is good for the company, right? I mean, the company doesn't want a whole lot of boxes overweight because that's like free Cheez-Its. I do like Cheetos though. And then, they also don't want boxes underweight because, they got to label their boxes what they are and they don't want to lie to their customers. So, pretty good problem, and it shows how it's actually utilized so easily here. And, but you got to be careful. The only thing I'm going to continue to emphasize is the work that you have to show, and that's just exactly what I did here, talking about what the question's asking, both in terms of Cheez-Its and z-scores, and then giving your answer. You don't have to write normal CDF or anything like that. You just got to, show the work for z-scores, because if you're going to use normal CDF, you got to use z-scores. All right, and the cool thing is we can also work backwards. You might be like, work backwards? What are you talking about? Well, what if we're given the proportion or percentage of data above or below a value? And we want to use that knowledge to find the value that you're talking about. Okay, let me show you what I'm talking about. That's a little bit confusing, but it'll make a lot of sense here in a minute. So if I say, hey, what z-score has 15% below it? What z-score has 15% below it? Well, because of symmetry, we know that the mean has exactly 50% below it. So it's got to be something lower, right? And, if we look below -1, we know that there is, a decent amount of data below -1. Not a ton, but, there's a decent proportion there. But I want to know exactly, right? Exactly what z-score has precisely 15% below it. Or another question I could ask you is, what z-score has 34% above it? So once again, I know that the mean right there in the middle has 50% above it. That's a z-score of 0. And, where's the 34%? It's easy to cut this in half and see 50-50. What mark has 34% above it, which would be equivalent to 66 below? Where's that at? Is that right around here maybe? I don't know is the point, right? Well, I'm going to teach you how we could find that using our fancy dancy calculators. And again, let me just repeat, same thing over here, right? I'm trying to find the z-score 15% below it. So I'm trying to find the mark that is 15% to the left, 85% to the right. Where's that mark at? Well, to do that, we have to once again go back to our TI-84s. This time we're going to hit second vars, and right underneath normal CDF, you should see invert norm. Now, here's what the invert norm screen looks like as long as you have your stat wizards on. And the first thing it asks for is the area. In fact, the first and only thing it asks for is the area. Now, the only thing you got to be careful of is two things. One, you got to type it in as a decimal, right? You're not going to type in 15%. You're going to type in 0.15. And the second thing that is by far the most important is that the area that you type in has to be the proportion below. Has to be. It's just how it works. Sorry. Now, we're always going to leave the mean at 0 and the standard deviation at 1 because that keeps us universal. All things are put onto that universal Z-score scale. And all we got to do is hit enter twice, and it's going to give us the Z-score with that proportion below it, right? So this will give us the Z-score we're looking for. So let's come back to here, right? I want the Z-score with 15% below it. So all I got to do is go second vars, select invert norm. Now, the percent below, that's exactly what they mean by area. So I'm going to put 0.15 here. And guys, that's it. Leave everything else at 0 and 1. Hit paste. And this is the Z-score that has 15% below it, negative 1.0364. So negative, I was pretty close, right? So it's actually going to be, let me erase this for a second so I can actually show you this real nice. So negative 1.0364 is going to be right about here. So there's 15% below that, 85% below that Z-score. So it's pretty cool that the calculator can locate that Z-score for you. All right, let's do this next one here. Let me do a little bit of erasing here first. All right, this time we want to know what Z-score has 34% above it. So this is where we got to be very careful. All right, the calculator does not work with above. It only works with below. So you need to have a common understanding that if I'm talking about 34% above, that is equivalent to 66% below. So when I go and grab my invert norm here, I am going to be very careful. I got to type in 0.66. It only wants the proportion below, not above. All right, so I'm going to go ahead and hit paste here. And it gets 0.4125. So that's a Z-score of 0.4125. So here's 0, here's 1. 0.4125 is approximately right here. That's going to have 34% above it, 66% below it. Boom, there's the Z-score I'm looking for. So those are the two huge commands that your calculator does when it comes to working with Z-scores and the normal model. We're going to use normal CDF and invert norm a ton. Let's go back to an actual real problem now. All right, back to Cheez-Its. Mean 16.2 ounces. Let's officially write that down. Standard deviation sigma. I almost put an S there. Sorry, this is normal. This is just a model, right? This is just parameters for all Cheez-It boxes, 0.2 ounces. Okay. What weight has 20% above it? All right. So, if you draw my picture, I'm trying to find the weight with 20% above it. Okay. So I'm just going to kind of draw, roughly maybe right around here, right? 20% above it, which means 80% below it. And that's huge because remember, that's what invert norm wants. So the first thing I got to do is I got to get a Z-score. I got to figure out what Z-score marks the top 20% and the bottom 80%. So I'm going to go back here. I'm going to go ahead and grab invert norm. I'm going to do 0.80, so be very careful that you always put in the bottom. Even if they tie the top, you might have to do a little bit of math in your head real quick. All right, and we get 0.8416. So a Z-score of 0.8416 is the Z-score I'm looking for. But that's a Z-score. That's how many standard deviations from the mean. I'm looking for the actual weight. So then what you have to do is you have to set this equal to the Z-score formula. The Z-score formula is the individual weight minus the mean divided by the standard deviation. So what I'm going to do here is I'm actually going to solve for x. Because what I'm doing is I'm working backwards, right? I know the mean, I know the standard deviation, and now I know the Z-score. This is a very specific Z-score that marks that top 20%, bottom 80%. Now I got to solve for it. It's actually really quick math. Shouldn't take you too long. First step is to take the 0.8416, multiply by the standard deviation, multiply the 0.2 over, and then add the 16.2, and you get 16.37. So the individual value is 16.37 ounces. So I basically was taking a Z-score and converting it back to an actual weight, whereas prior we were taking a weight and converting it to a Z-score. Pretty cool. So this is the weight that represents the top 20% of boxes or the bottom 80%, same thing. All right, final question here. What is the first quartile of Cheez-Its weights? Well, here we have to remember what first quartile means. The first quartile is a very specific vocabulary term that means the bottom 25%. Oh, the bottom 25%? Oh, well, my goodness, that's exactly what invert norm does for us. Invert norm, we're going to put in the 0.25, the bottom 25%. And this is the Z-score that represents the bottom 25%. So the Z-score that represents the bottom 25%, sorry for taking it away so fast there, is 0.6745. Negative 0.6745. And that, again, let's keep in mind that has 25% below it and 75% above it, but invert norm only wants the below. And now what I have to do is, that's a Z-score, that's how many standard deviations from the mean. I now have to solve for what actual value represents that. So I'm going to take the Z-score and set it equal to the formula for a Z-score, and I'm going to quickly solve here. So I'm going to go ahead, I'm going to take negative 0.67. You don't have to really show any work here. I mean, come on, you guys are in AP stats. You should be able to solve this very easy equation by multiplying by 0.2, adding the 16.2, and I get 16.07. 16.07 ounces. So that would represent the first quartile. So 25% of boxes is going to be below that. 75% of boxes are going to be above that. So pretty cool thing that you could do. And this is all the power of if you're a normal distribution. None of this math could be done if we didn't know that Cheez-Its followed a normal distribution. And let's look at one more use. This is one more topic that you need to know how to do. You got to be able to rank. Now, this is actually a pretty cool activity. So I want to rank these three things from smallest to largest. The problem is, one's given to you as a third quartile, B is given the Z-score, and C is given a percent, right? So A is the third quartile, and this is for any random set of data that follows a normal model. So we got the third quartile, we got a Z-score of 0.8, and we got 20% above it. Now, it would be really easy to rank these if they were all Z-scores. So B is already a Z-score. That means that value B is 0.8 standard deviations above the mean, so just a little bit above the mean. So what would the third quartile be? I want the Z-score for the third quartile. Well, let me think about that vocabulary word. The third quartile is the 75th percentile. 75% of data is below it. So all I got to do is grab invert norm, and I'm going to put in here 0.75 because that's what the third quartile is, the bottom 75% of data. And I get a Z-score of positive 0.6745. 0.6745. So now I could clearly see that A is smaller than B. And then I need the Z-score for the value with 20% above it. Well, okay, now I got to remember, invert norm doesn't do above, invert norm only does below. Well, if I want the bottom or the top 20%, that is the same thing as the bottom 80%. So I'm going to go back here and do 0.80. And again, that simultaneously is talking about the same thing, 20% above, 80% below. But just again, I can't say this enough. Invert norm only wants the below. And this is going to give me the Z-score that I'm looking for, 0.8416. All right, now I can officially rank these. The lowest is A, the middle is B, and the highest is C. So it is in alphabetical order. It didn't necessarily mean for that to happen. But the key thing was understand that you can only compare these three things if they're all in terms of the same value, which is a Z-score. So make sure you know how to calculate these Z-scores with the power of our calculator. All right, guys, that's it for this video. I know it's kind of long, but normal models are so awesome, and we're going to use them the whole year. So it's super important that you understand all of them.